Okay, can you listen to me? Okay? Yes? Well, hi everyone. My name is Bárbara Rojas-Ayala. I'm from Chile. I'm from the Universidad de Tarapacá. And I want to thank the SOC for inviting me to give this talk. Because I'm really excited about with all of what is happening in this field. I remember when was my first Gold Star. I was a grad student. I just had come to the States. And I remember that no one was working in what I was working, that was trying to get metallicities of M dwarfs. And now clearly that thing has changed a lot. So most of the things that I'm going to talk about are things that you have been done in the past 20 years. I want to thank also the Institute and Kata for providing the funding for me to be here. So, during the past 3 days, we have been hearing about multiplicity of M dwarfs, ages, H alpha, masses, sizes, kinematics, a lot of stuff. But we haven't heard much about spectroscopic characterization, in particular, what it is with effective temperatures, log G, and metallicities. So I'm going to focus on that. And in a nutshell, I'm not going to do like what I'm going to talk about, but basically this is my final slide. It's basically telling you that there has been a huge progress in the last decades. And this is mostly due to surveys that now are going deep enough to get a bunch of M dwarfs and the exoplanets that were starting to be found in the early 2000s around these stars. There are different methods or techniques and different regimes where these things, methodologies works. There are still a lot of things to do. I'm going to warn you that this is my vision on the field. So I'm going to give some ideas of what I think are still being missing in our field. So what are M dwarfs? M dwarfs are those red dots that you see in that figure. This is a figure from the Slowpokes catalog from the et al. In 2010. And those red dots, that's why M dwarfs are also known as red dwarfs, right? What we have here, it's a color magnitude diagram where we can see the Gaia catalog of nearby stars and highlighted the stars within 10 parsecs that Celine showed us, I think 2 days ago. And we can see there that M dwarfs, those red dots, cover quite a large, wide range in magnitude. They're way fainter than stars like the sun, and also in color, way much more than any other spectral type of stars. Okay, so I'm talking about stars, not about the brown dwarfs, because then things get fainter and also cover a large range of colors. However, the results, these results that we see here in this plot are from Gaia, and it's great. Now we have a lot of parallaxes for a lot of M dwarfs that we didn't have before because Hipparcos didn't have many of them because M dwarfs are intrinsically faint. However, for the 10 parsec sample, we did have some parallax for recons, and I want to recognize that basically this highlighted plot is something that we already had when, for example, I was starting my PhD. Now, M dwarfs, when we talk about a spectral typing, like looking at the spectra, are the stars that have titanium oxide or molecular absorption. Here I'm showing some SCDs from Sandy Leggett's paper, where we can see what's happening with M dwarfs. And if you have seen a solar type spectra, you will realize that here there is a lot of absorption. In the optical, mainly due to titanium oxide, vanadium oxide, calcium hydride, and in the near infrared, you have CO, water, iron hydride. And this has been kind of difficult to deal with when we wanted to estimate things like metallicity. One of the superpowers that M dwarfs have, I like to think of it that way, is that basically they are, quotes, immortal. in which sense is that they reach the main sequence and they stay there basically forever, if we consider forever, the current age of our universe, right? None of them has evolved. So if we want to study something about the galaxy, this will be the perfect objects that we should go and look for to study, for example, the chemistry and everything, right? They haven't evolved. They basically remain doing the same. So why do we want to study M dwarfs? There are several reasons. I tried to look in the literature why we were doing this. Well, I guess one of the things that we all know is that they are the largest stellar population of the galaxy. They're about 2/3 of the stars in our galaxy. As I said before, they have long main sequence lifetimes, so they're perfect to study galactic structure and evolution. This is something that we saw during the Tuesday talks. And this is great now because we have these large, deep surveys that are not only getting photometry or low resolution spectra in the optical for M dwarfs, but we are also getting high resolution spectra in the near infrared, for example, with apogee. Another reason, it's basically the exoplanet science. It was early in the searches for planets with RVs, with RV technique, that we start finding planets around M dwarfs. And we wanted to know their characteristics. We wanted to know the characteristics to select them for new surveys. We have the star-planet connection. We know that if you don't know the star, you really don't know the properties of the planets. And because of their astrobiological potential, right? Like this is something that we want to know. And the third reason, it's because we need benchmarks. We need stars that will help us get stellar models better. And M dwarfs are the transition between what it is a star and what it is not a star, right? And also because of magnetic activity. And well, this is something that we saw on Monday. So since I'm going to start talking about spectra, I want to show you this very early work from Mould in 1975. And this is probably one of the first grids, model grids of M dwarfs, where you can see the opacities that were being considered with titanium oxide, water, and CO. And there is a sentence in this paper that I think it still holds now, that we really want to have really good synthetic models, that they are precise enough and they have enough detail for us to get all the information that we can want from these M dwarfs. So I knew that I only had 25 minutes for this talk, and I was like, okay, let's go and try to figure it out. What are the important papers, articles for this field? So I had a BibTeX with about 41 articles that are related to parameters from spectra for M dwarfs that range from 1975 up to 2024. And I put it in this app that it's Citation Geeko that appeared to me in Twitter. And I was like, let's try to figure it out if it actually can guess it right, what I thought were the most important papers. So what you have here in this figure, it's the yellow dots are the seed papers. So those are the 41 papers that I had in my BibTeX. And the black dots are the papers that are being cited in those seed papers. Okay, so they're not the citations to those papers, but are the citations that are within those papers. And if the black dot gets bigger, that means that several papers are citing that work. And I wonder if you can guess which ones are those works. So probably you would not, right? Like, so these are papers that are related to spectroscopic parameters of M dwarfs, okay? So I highlighted in colors the ones that had the largest dots. And you can see right there at the top that one of the most important papers is about abundances of FJK stars. But this work These were for M stars. So why is that important, right? And this is the Valentian-Fisher 2005. This is the spots catalog. And maybe for the very young students here, they have no idea what I'm talking about. But I was starting my PhD, and this paper was fundamental to get basically metallicities of M dwarfs, and you will see now why. The largest dot, it's about metallicities of M dwarfs, something that, maybe was expected. But what is interesting is that actually it's not a spectroscopic paper, but if you look at it, it's actually a color magnitude diagram. And that actually shows how desperate we were trying to get metallicities of M dwarfs. Okay, then the other two, it's related to interferometry. This is something that also was coming out during that time. It's also a thesis. This is Tavi Bojayan's work, trying to get angular sizes of as much M dwarfs as possible with the Charter array. And then we have the fundamental parameters and these relations of Matt et al. In 2015. And in this case, it's just 2015. And this actually shows that we needed calibrators. Okay, if we want to know the properties of M dwarfs, a lot of the work has been done with calibrators. Why is that? Well, because when I started my PhD, what we knew about metallicities of M dwarfs was mainly due to low-res optical spectra by measuring indices of titanium oxide and calcium hydride, and with this scale, the Zeta index, that basically divides M dwarfs in dwarfs, subdwarfs, extreme subdwarfs, and ultra subdwarfs. And this is because when the stars get metal poor, it's harder basically to do a molecule that includes two metals. So titanium oxide basically disappears, but since there is a plenty of hydrogen in the star, you can still, for example, have the hydrides. And this is basically the metallicity classes. You can see the papers right there. This was used as a proxy for metallicity. It was quite useful when we were looking at the galaxy, being the subdwarfs tell us things about the halo. At that time, there were also very brave people trying to get metallicities for M dwarfs using high-resolution optical spectra. At that time, since M dwarfs are very faint, there weren't many stars because they're full of molecules. It's hard to identify those lines. The iron lines then become iron hydride. It's a mess. You don't know where the continuum is. And also because, for example, this work of Wolf and Wallerstein use, for example, binary systems, an FJK star with an M, and try to see if the abundances of iron were the same, and find disagreements for temperatures below 3,500 Kelvin. So then I want to highlight here the important role of binaries. We know this. The only way that we can get reliable masses are by using binaries, and I show here a plot of the mass-radius relationship. But also binaries were fundamental to calibrate metallicity relationships for M dwarfs, under the assumption that these systems were formed at the same time from the same material. So when you read papers from 2005, maybe to 2010, you will find these, objects being coeval. And we are going to assign the metallicity of the hotter component to the M dwarf, and then we're going to try to find something, an index, a color, whatever, that will let us know the metallicity of the object. I say binaries, but actually we were using common proper motion pairs, mostly from the SuperBlink catalog of the work of Sebastian Lepine. So we assumed that they were binaries, but we weren't really sure that they were binaries, okay? So that is when we got really creative. I'm showing you again a color magnitude plot right here. This is from the Johnson and Apps paper, where they basically put a line in the middle of this plot and divide it between being solar metal rich and metal poor, and they highlighted the planets there. And why they highlighted the planets? Because at the time we really wanted to know if M dwarfs were also following what was being seen by Santos and Fisher and Valenti, that planets were being found around metal-rich stars. At that time, most of the giant planets were being found, so the planet-metallicity relation for giants was holding, and we wanted to know if that actually was the case for M dwarfs. M dwarfs are already different, we treat them different, we need different methodologies, maybe they also create planets differently. And what you have in this side, it's the work that I did for my dissertation that was using near-infrared spectra. That at the time it was mid-resolution, now it's low resolution. Yes, that's another thing, right? We have now high-resolution near-infrared spectrographs that work pretty well. And I based this basically with indices measuring the fluxes of sodium and calcium with this index that was measuring how the spectra bends when you go into lower temperatures due to water, trying to also get metallicities of this. And we figured out that yes, the stars that have, the M dwarfs that have giants were indeed more metal rich than the ones that didn't have any planets, or they have terrestrial planets with very small samples. This work, using the low resolution near infrared, then was looked out by other theses. We have Terrien, Mann, and Newton that use specs. I was using triple spec, so they even went to even lower resolutions to get the fundamental parameters of M dwarfs. And this is when I want to highlight another of the important things that was highlighted in this image that I show you about the important papers in the literature, that it is angular sizes for low mass stars. This is the thesis of Tavi Bojayan, where she went to look for all the stars that she could observe with Chara in order to get the sizes. The angular sizes with distances, she was able to get the physical sizes of these objects. And if you have the volumetric flux, you can get temperatures. And Mann et al. Very smartly used all of this information to create these two beautiful papers about how to constrain your M dwarf. And if you work in exoplanets, you probably use these relationships all the time. And this is based on low resolution near infrared spectra in values of interferometric measurements. You should go, and this is basically what everybody is using. However, we wanted more, and I'm really happy that very brave people decided to continue to work with high resolution spectra, not only in the optical, but also because M dwarfs became so important to find this second Earth, these small planets, because of the Ember Opportunity. There were spectrographs built to find those ones in the near infrared, in the optical. An example of those ones is Carmenes. We have Spirou, we have NIRPs. At the time where I was starting my dissertation, Critus was at the VLT. It was a pain to deal with Critus. So very brave people wanted to get stuff with that instrument. But here, for example, I show you examples of synthesis of high res spectra. The results from, for example, from Marfil with Carmenes. And here I show you some stuff that we did for the thesis of Pedro Sarmento with Apogee. There were other ones done here, but I'm going to go into it later. And also, I encourage you to go today to the Splinter about planet hosts and around planet host cool dwarfs. Yes, that's what it is. Where they're gonna talk about something that I think it's amazing, that now we can get abundances for M dwarfs. This is something that I never thought it was gonna happen when I was doing my dissertation. But now we can do this. Why? Well, because we have Apogee and the beautiful work of Diogo Soto that has been doing with all of that data. Now we can measure different elements, put them in comparison with solar type stars and see the trends, for example, that we have in the galaxy. We have here the work of Maldonado et al. Using PCA. In this case, maybe he can correct me, but I think he still uses FJK stars to constrain metallicities, for example. And here we have another work using the, I forgot the instrument, but it's in Subaru, high resolution spectrograph. IRD, thank you. Measuring, for example, the abundances for all the elements here, they're ordered by atomic number. So this is great. Now we can finally put M dwarfs and FJK stars in the same scale and not treat them differently. So this is amazing. There's also something else, right? Now, when I was doing my dissertation, there was too little data. Now we have too much data. And we need to deal with it. And one of the things that we want to do is use, these data-driven methods. Why? Well, we have so much data. It's impossible to go one by one, line-to-line analysis. So we want these things to work. I have an example here from Birki et al. 2020 with Apogee and the Canon, where they fix log G and estimated temperatures and metallicities using the binaries that Mann et al. Use for the calibration of metallicities in low resolution. And here I want to highlight the work of Adam Rines, that it's not using high resolution, it's actually using low resolution optical. But we can use these methods in order to get stuff out of these ones if we're very careful on how we use our training sample, our benchmarks. So I encourage you to go and look at this work. I think he's going to present this also in the other meeting. And here there are other works, and well, I highlighted the talk of Aida she gave on Tuesday. So I think I still have 3 minutes left. So this is what I think it's still missing. Okay, and you can, probably some of you are already working on this, and please contact me. I really want to know what you guys are doing. But what I think is still missing. So the first thing is that we're missing the cooler M dwarfs. Most of the techniques seem to work well from M0 to M4, maybe to some claim to M7, but I put that in doubt, basically because most of them are based on benchmarks, and we don't have so many benchmarks that are that cool. Because when we do this in near infrared, at least the work that I've been done in high resolution, normalization plays a huge role in how we're getting the stuff. We're missing line lists. Hopefully that will work for the optical to the near infrared. So if you're working on that, please let me know. Another thing is that we need more benchmarks. And that means that we maybe need to use new instrumentation in order to get more sizes, with the big telescopes, because it's okay. I know that this is all what we have, right? So basically we use calibrators to calibrate our stuff, and then we use those stars in order to say that, yes, things are working. And it's because we don't have anything else that we can use. As it was pointed out in other talks, like if we want to use data-driven models, we really need to have really good calibrators, and not just a few, but a lot of them, right? I didn't even put that there. So I said, well, we don't have the cool M dwarfs. There's no sub-dwarfs, and there's no young stars either, right? So we want that. What about log G? This is quite interesting. A lot of us didn't want to deal with this because the problem gets really degenerated, but we're missing measurements of log Gs for stars that make sense. And some of us that have been involved in exoplanet stuff, we say, yeah, we get temperatures from this side and metallicities using this, but no, for log Gs, we go and use this other technique and things don't necessarily converge, okay? Just so everything looks nice. And the last part is, I think we all have been doing a really good job trying to compare values to values. But one thing, it's being more clear about what we have with observational and theoretical approaches, but also between different techniques. specifically the optical and the near infrared, but not only compare values to values, but really try to use maybe the same spectra and try the techniques on that spectra. And I'm out of time, but I just want to highlight here there is a problem with log Gs. So go and check this out. With Sarmento et al., we wanted to do everything without calibrators. So this is really like synthesis like we do in solar type stars that you have there and how they don't really agree with evolutionary models. And I want to point out here the work done with Espiru data of Cristofari, well, it's around here, where he sees that, you know, he cannot really get the log Gs that is expected from other relationships, but he gets really good fits from temperature and metallicity, for example. And this is another work that I want to highlight related to what if we use the same data and test different techniques. This is a work led by Pasager et al., where we tested different things. Please go and see it because I don't have much time, or you can ask me about it later. And since I already showed you my conclusions, I think it's there, and I'd be happy to take your questions. Thank you. 1 minute. 1 minute.
Please repeat the question for the remember to ask questions. It's important. And
Ulrich has a question too. Ulrich.
Hello, Ulrich from Uppsala University. Thanks very much for the talk. I would just ask, do you have any ideas how to go forward with the Dog-G methods? What would your, which direction?
Okay, so Ulrich was asking if I have any ideas about log Gs, like what we can do with that. Well, we saw, for example, examples, I think it was on Tuesday, I don't remember if it was yesterday or Tuesday, using not just the spectra, but maybe use other data. I think Tonali, for example, is doing something like that. The tool that it was, yes, there it is. I think it's great that now we have, you know, this whole Bayesian stuff where we can have some priors, maybe give a smart priors. We know that maybe models, evolutionary models, maybe are not fitting perfectly what we calculate. But we know that that's what we know, right? Like that's physics that we know. So maybe we can figure it out, ways to give information that is just not fixed, but maybe that it's what it should be expected from the physics that we know. So that's one of the things that I can think of. Inspect different data. I know that it would be great if we could find oscillations around M dwarfs. We haven't been able to find that. But I don't know, maybe, you know, in the splinter today, we can maybe start thinking about what we can do in order to constrain those log Gs and get those values to get estimates of masses if we have the radius. Hi.
Rafael from Santiago, Chile. So you mentioned that the planets are expected to be around metal-rich stars, not metal-poor stars. So if you follow the models are suggesting that even in a primordial case where the metallicity is 0, you can form down dwarfs for the deuterium chemistry.
Yeah.
So intermediate case is a metal poor. So why we should not expect planets around that?
Yeah, sorry. I'm going to repeat the question. He was asking why we're not. I was saying that we don't find planets around metal poor stars. Yeah, sorry, that's not what I wanted to say. I wanted to put this in the context of 2005, where there was the results of the planet metallicity correlation. At that time, I don't see the person that asked the question. Jose? Yes, thank you. So I want to answer to him. Thank you. In 2005, what it was, most of the planets being discovered around solar type stars were giants. weren't these small planets at all. So the planet metallitic correlation was basically very biased towards these giant planets. We know now that that relationship holds for giant planets in FJK stars. In M dwarfs, giants are not that common. They are few. The first M dwarfs nearby were discovered, like Gliese 876, Gliese 8. Oh, I forgot now the names. I used to know them all. They're not that common. However, we're finding giants, but not so close, farther away. So now we know that all stars with independent of metallicity, they can have planets, but there is a discussion if they actually can have giant planets. But I understand what you're saying, right? Brown dwarfs can't form even, so if giant planets are not formed by the co-accretion scenario, yes, you could have a giant in a very metal poor star.
Thank you. Let's bring Bárbara again.
Thank you.
The next speaker